Do I start? No? He's going to give me the signal. All right, so I've been given the signal to start. Okay, so I'd like to welcome our very special seminar speaker today, Steve Sherwood, who I've known for some time, and I'll give you a little rundown, his little background, as much as I can remember. His topic today is on I guess I've been in the field for a long time, but it seems to me that the modelling, Earth climate modelling and Earth system modelling has been kind of progressing, but not in leaps and bounds. And obviously in the last couple of years, the last couple of 5 years or so, and what we expect in a decade, we're going to see major changes, I think, in the way we think about modelling the Earth system and climate models. And Steve's going to tell us a little bit about why traditional climate models isn't a thing of the past, and why and how they might be improved. And things are changing. With the resolution of models are changing, the emergence of machine learning, and so on is going to change the landscape of modelling. And Steve's going to kind of give us his pioneering thoughts on that topic. Steve has. I've known Steve since he was a student at Scripps, PhD student at Scripps. Before that, he did his bachelor's at MIT. His PhD at Scripps. He had postdoc positions, went to New Zealand of all places, and had a NASA postdoc, and spent some time, became a professor at Yale. I can't remember exactly how long you were at Yale for.
8 years.
Huh? 8 years? Wow, was it that long? Wow. Okay, and then.
I'm old.
I know you're
not as old as you.
No, you're not as old as me, but you're getting old. I guess it would be sometime in the early 2000s, you went to Australia, right? University of New South Wales? What year was that?
2009.
Okay, 2009. 2009, University of New South Wales, and he's been there ever since, and has been a leader of the University of New South Wales Climate Change Research Centre, director of that and deputy director of that, and has been heavily involved in other major climate initiatives with Australia currently. And, of course, has been a lead author in the IPCC, and currently he co-chairs the World Climate Research Program Safe Landing, which is about, how we might quantify risk and identify pathways to, address, living in the world of risk. So with that, Steve, we welcome you, and really look forward to this seminar. Thank you.
Okay, thanks very much, Graham. Can everybody hear me? Good. Yeah, it's nice to be back in Pasadena. I was actually born at Huntington down the road, and moved away when I was 7. But it's fun to come back, and I appreciate you guys arranging a winter storm so that the air would be cleared out and the mountains would be gorgeous. It's been really reminded me how beautiful it is here. Just for me, yeah. Thanks very much for that. So yes, Graham told me what I'm going to talk about. Told you what I'm going to talk about. A few years ago, I led a big effort to try to better quantify climate sensitivity. And so sometimes people, last week somebody asked me why I'm not working on that anymore. And I said, well, I kind of am. Because one of the things that we came up with, I think, doing that review, one of the conclusions I came away with is that maybe the biggest or one of the biggest impediments to figuring out what climate sensitivity is the fact that the climate that we need, we have all this evidence from past climate changes and from observing how clouds work, but all of that evidence, in order to interpret it in terms of climate sensitivity, you need a model to map from one to the other, to link the evidence to sensitivity and therefore to the future. You can't observe the future directly. And our models weren't really up to it. They do things wrong. You can always get whatever global average temperature you want, but then the pattern isn't right. And the pattern relates to feedbacks. And so then there was always a lack of confidence that we could interpret the evidence correctly. And so I think we really need to do better on models. So that's the point of what I'm going to be talking about today. And why is it buzzing instead of going forward? Oh.
We're having a technical glitch. The slides aren't on screen as yet, so Quincy's in there trying to.
Oh, okay. That's. I'll just wait then. Slides are coming. All right, what else can I say? I thought I was already talking too long on this slide. If am I going to get a signal saying it's all okay? It works. Okay, great. So if you want to know more about what I think about climate sensitivity after a few years, I've got a commentary just coming out. Very fun paper to cite. I've been meaning to write a paper with Chris for a long time. And that gives sort of an update on our views of where we think climate sensitivity is and where it's heading. But we definitely need better models. So there's a number of persistent problems, and this is not an exhaustive list. It's just sort of some ideas I thought up. We know that it rains too early in the day. We've got a double ITCZ bias, which Bezoon here is very interested in. Drizzle bias, which Graham pointed out in a very highly cited paper. The intraseasonal variability is poor generally. And of interest to climate sensitivity, they don't reproduce the heterogeneous warming pattern that we've had since the 1980s. Models say it should be much more homogeneous than what we observe. Same thing in paleoclimates. The models tend to predict a more uniform temperature change compared to the strong polar implication that is suggested by the observations. There's also this interesting thing called the predictability paradox, where models seem to be less predictable at high latitudes in terms of things like the NAO than the real world. You can average a bunch of model predictions, and it'll match the real world better than it matches any of the individual model realizations. So there's something funny going on. Decadal variability of things like drought is also bad. And these are important things. So for example, the drought that you're having now, well, I'll talk about that in a minute, the prediction of it is really affected by these problems. Okay. Now, most of you probably know how our models are created. We have a grid, a numerical grid that we put around the Earth. And then the problem is that we can't afford the grid to resolve everything. So inside one grid box, you've got a lot of things going on. Regional variations in topography, clouds that are smaller than a grid box, and so forth, turbulence. And what I'm going to be talking about is what we do about these processes. There's also the issue of how you take a grid box average and downscale it to all those different parts of the grid box, like the catchments and so on. That's not something I'm going to talk about, except briefly to allude to later on. So I would argue that the way we treat those things in models has developed pretty slowly. And there's 4 reasons for that. I'm not a model developer, but I've sort of been around a while, and my impression is that these are the problems. One is that those phenomena are very complex, and we really, if you look at how they're represented, it's extremely simple idealizations, for example, of turbulent processes, of land and ocean tiles, and so on. And we need to do that, but I think we often lack enough fundamental understanding to know the right way to simplify it. So that's a problem. It's a lot of work to build a scheme and get it to work, and get it incorporated into a model and tested. It typically takes a couple of years to do that, or at least it has in the past. And then we have the problem that if you write one and you want to evaluate it, evaluating it offline is hampered by a lack of data, especially for atmospheric processes like convection, where we really don't have observations of the things that a convective scheme is meant to predict. So that makes it very hard to evaluate it offline. You can build the representation into the model and try to evaluate it online. But then the problem you have is that there's so many problems in the model that you get compensating errors. And so you can change one thing, and it might make the model a little better. But then if you change something else in the model, it might get worse again. So it's very hard to do any sort of gradient descent operation to try to find a good model because so many things are going on at one time. So I'm going to get back later to some ways that I think we could get around this. Okay, but what many people are talking about now, one of the debates that I will wade into, is we can just go to higher resolution so that we don't have to parameterize these things anymore. And so this is a figure from the Diamond project. Raise your hand if you know about this project. All right, maybe half of you know about this project. So these tiles here are snapshots from different models that have been run at grid resolutions of 5 kilometers or less, which is much finer than a standard climate model. One of them is a satellite image. Since you guys are all at JPL, you should be able to know which one it is, but I won't ask you to guess. I think it's the one in the middle. But anyway, it's, yeah, I don't even know. Can't tell. They're so good, I can't tell. But you know, they actually are all different. If you look at these, the way they render these systems are quite different. Anyway, so this is a really exciting development, the fact that we can model the whole world at this kind of resolution. But I'm going to argue that I don't think this is the solution to our problems, even though it's an interesting research direction to go in. And one of the things is a real benefit of this, we're not resolving everything, but we're resolving organized convection in the atmosphere, at least on paper. We're doing that. So tick, that should be an advantage. But here's a paper by Feng et al. It took a while to do this analysis, I think, because these data sets are really hard to work with. But they're counting how many convective systems are in each one of these simulations. And there's about a factor of 3 or so variation in the number of convective systems between one of these high-resolution models and the next. And some of them are close to the observational estimate, which is good. But then when you look at the rain rate histogram here, all of the models are producing too much heavy precipitation compared to what they're calling observations here, which is the iMerge product, which is a satellite product that some of you probably know way more about than I do. Now, when I see something like this, I kind of wonder, well, maybe the iMerge is just wrong. But we happen to have had a student working in our center who compared iMerge to a radar product. And yes, iMerge was showing a bit less extreme precipitation than the radar product, but it wasn't as big of a difference as these differences shown here between the black line and all the colored ones. So it seems that all of these models overpredict heavy precipitation, and that's actually not a huge surprise because in small domain simulations with these sorts of models, this has been seen for years. And it's probably because you're not resolving shallow convection, and therefore you might build up too much instability, and so when you finally do get your deep convection, it's too strong and you get too much rain. So in other words, these models are not yet solving even the convective organization problem that they nominally should be able to resolve. But it's worse than that, because if you want to resolve things like downdrafts, you're nowhere near what you need to be at a 5-kilometer resolution. So this is from a study that was done by a postdoc working for me. We're trying to understand the dynamics of downdrafts and what this is a simulation of a downdraft that produced the strongest observed wind gust in Sydney over the last 20 years, which was a pretty successful simulation using WRF, but only if you run it at a resolution of 200 meters. If you run at 1 kilometer, you lose a lot of the downdraft. If you run at 5 kilometers, you get nothing. So it shows that although global CRMs are improving on a few things, they're not coming anywhere close yet to resolving all of the physics that we need to capture to get things like feedbacks and stuff right. And even if you could resolve this, then there would be even smaller scales at the surface layer that you wouldn't resolve. So it's kind of a tough problem. Okay, and there have been some interesting commentaries on this, including one written, this one, and another one that Tapio Schneider led not too long ago. also making the argument that maybe it's not worth trying to resolve everything. And the problem really comes down to computing power. Every time you go to try to reduce your grid by 1 order of magnitude, the amount of computing power you need goes up by about 3 orders of magnitude. And so the mathematics of this is really crushing. If you had the same amount of computer power and used it at these 3 grid spacings, at 100 meters you could run for 3 days, at a kilometer you could run for a year, and at a typical traditional model resolution you could simulate the last glacial cycle 10 times. So if you think about it, no matter how, even as computers get faster, we're going to have to wait an awfully long time before we can do this. But well before we get to that point, we'll be able to do these amazing new things with relevant to paleoclimate with the models that we have now. So which brings me to the question, what do we want the models for? Okay, and we're thinking about this in the lighthouse that Graham mentioned. And in Australia, because this is a small country, we do talk to stakeholders a bit in the universities. And the kinds of questions that the users of climate information have are things like, should we build a desalination plant in Melbourne or not? Should we raise the Warragamba Dam in New South Wales or not? Or how much should we raise it? And these come down to questions of things like drought risk. How likely are we to have a drought that's worse than any of the ones we've seen so far? And to answer questions like that, you need paleo data. You need to consider long time scales. If you're using models, you have to run them for a long time. And they have to have good coupling with the land surface, because otherwise you're not going to get things like drought. And they're going to need to have accurate regional patterns, because, for example, the drought that you're having now in southwest United States is probably connected less to global warming than it is to the regional patterns in the Pacific that have been happening, which models don't really do a very good job getting right. So there's a lot of issues there. If you're interested in flood risk, you also need, if you want to know what's the chances of the storm you had last week, they were calling it the storm of the century. I don't know if it's really a 100-year event, but what we have all around the world, we're having extreme events that we're wondering, could it be even worse than this in the future? Or is this the worst we'll ever have? So same thing, you need to consider long time scales, big ensembles. High resolution would certainly help with this one, but it's not enough. And if we wanted to consider bushfire risk, similar issues come up. So for all of these things that we're worried about, we have to worry about coupling in the system, coupling to land surface, coupling to humans and human responses. And so my view is that going to high resolution simulations is not going to help you deal with any of these problems, because you just can't afford to do any of these things that you need to do. And if you don't even know whether the Southeast Pacific is going to warm up or not, that determines the boundary condition on any high resolution simulation that you did for the United States. So what would be the point of doing a finely resolved simulation that's got the wrong boundary conditions, or we don't know what the boundary conditions are? So I think that where this leads me is that we really need to do what we can to make the global models that you can afford to run for a long time better, so that you can afford to do all of these things. So just a little plug for our lighthouse. This is one of the things that we're thinking about. And we've got tipping points is one thing that we're interested in, but also a lot of others. Tail risks in the climate system. How to quantify this, how to sort out the real risks from the ones that people are scared by, but they shouldn't be. And if you're interested in that, talk to me. There's a YouTube channel that shows some of the tipping point things that we've, discussion events that we've had. But this is just to show you that we will be needing to think about more coupling the system. Typically, we've just had these dark arrows here that we've thought about. But to answer a lot of the questions that we have about climate adaptation and land use and geoengineering and so on, we're going to have to start considering more things. And that gets, that's kind of going in a different direction from high resolution. So we need to learn how to do this in models that are good enough. So this brings us to the model of physics, which I would envision this way. We have all of our boxes in the model, each of which has things going on inside it. And what the global model is calculating is an average value for every one of these squares here. And at any given time step in the model, which is typically of order a half an hour in traditional models, those values can be updated because of the equations that you're solving, which might be bringing warm air in from the next grid box, for example, or from the processes that are going on inside the box. For example, they might be transporting warm air from the boundary layer to the middle and upper troposphere using motions that don't appear at the resolved grid scale of the model. And that would appear as a heat source up here and a heat sink down there. And that would be the second term here in this equation that I've got. So we need to know how to predict this term from the values x that the model knows about, the global model knows about. So we need to map the grid box average values onto whatever we need to know to predict those tendencies. This is what we've been having to do all this time. And so for the last few years in my group, we've been trying to go back and think about how to break this down in a way that might be more useful. And we've gone back to an idea from Jiming Kwong from more than a decade ago, where he computed a linear response function. So he basically linearized this operator that we're looking for here, this mapping. You can linearize it, and it turns into a matrix. So on the x-axis of this matrix is the level at which you would perturb the system, and on the y-axis is the level where it responds. Okay, so you can consider perturbing the system at every level, and for each of those perturbations, you can look at the vector of responses, and that should, in a linear sense, completely characterize how the physics work. And I forgot to put in a slide that shows actually how we do this, but we're doing it the same way that Jiming did, which is you have a regional, you have a single column model. And the reference is a cloud resolving model running in that column. And the perturbations are just maintained steadily for a long time, and you look at the time average response. And then you can make up this matrix. You would have to invert this matrix to get the mapping that I showed you before, but we're not going to worry about that. We're just going to look at the matrix itself, which you get just by doing the experiments. And you can do the same experiment in a single column model with GCM physics running in it. You know, pick your favorite convective scheme and put it in a single column model. You can do this with WRF, the model from NCAR. So that's what was done in this paper by my postdoc, Yiling Huang. And what she found was that what we're looking at here is the same experiment done in a bunch of with a bunch of different convective schemes. And we showed that it was the convective scheme that governs this particular response, not the other schemes in the model. With the numerical one that Jiming calculated up here. And I should also mention, this is from a model called SAM. We've repeated this now with two other models, WRF and the UK Met Office model, which is called Monk. And if you run them at high enough resolution, they give very similar results to this. So we're now confident, even though this is not an observation, it's only from a numerical model, we're pretty confident that it's close to what should happen. And so we would like our schemes that we use in the global models to behave the same as this. And it makes physical sense. The diagonal here is how much temperature change you get at the level that you heat. And the off-diagonal elements is how much change do you get at one level when you heat another level. And what it's telling us is is it below the level you heat, you tend to also get a temperature increase because you're making a little inversion. And above the level where you heat, you get less of a warming because also of that inversion means that the turbulence doesn't get through. And it also shows more warming as you go up, which makes sense from thermodynamics because of the release of latent heat. So it makes sense, and it's kind of a simple, smooth result. And what's interesting is that when you look at what happens in our current convective schemes, most of them do crazy stuff, especially the Met-Office model, but also a lot of the other ones. Some of them are close, but none of them do the right thing. So you can already see from an experiment like this that none of the model physics that we're using are behaving the way they should. But what's good about this is that you can diagnose problems. So this is a version of the French model, LMDZ, where they saw this blue blob. Notice that a few of these have blue blobs, and the numerical model doesn't have any blue blobs. They figured out that this was because of a mistake in the way they coded the re-evaporation of shallow precipitation, and they fixed it. And they got rid of most of the blue blob. It's still not perfect, but they improved it. And so that's the newer version of that model. So we actually led to a model improvement through this approach. Okay. Now, this approach that I just showed you is a steady response. It looks at the steady things that would happen in an idealized, linearized, small perturbation experiment. But a few studies have pointed out that convection appears to have a memory of past states such that you may not succeed by writing what the physics are doing as a function of the grid box average values at that same exact time. You may need to know what it was doing at previous time steps, because if there's turbulence, the turbulence doesn't just suddenly stop because the grid box values change. And this goes really back to some early work by Sterling and Petch from the Met Office and Laura Davis. But I had a student, Maxime Collin, who attacked this directly in his thesis and did a few experiments to look at it. And I think the most interesting experiment we did was where we used a single column model again with cloud resolving models, so kind of like the one Jimin Kwong did, better resolution. And what we did this time, instead of running it to steady state and doing small perturbations, we ran it in a way where we prevented the average over the domain from temperature and humidity from changing. In other words, that x state vector is artificially held fixed. Nobody would normally ever run a model this way, and he actually struggled to get it to work. But he did it. And so if it were true that you could do this, which is what almost all the models do, then the convection would just bubble away steadily and give you the answer that you get for that value of x, because we're not changing x. But what we actually found is that it didn't stay constant. Sometimes the convection just stopped. And so there's one of his simulations where the convection just stopped. And then, whoops, what happened to my other one? Oh, there it goes. OK. Then there's another one where the convection exponentially blows up. Almost exact same value of x. Okay, only the tiniest difference in x, and it either exponentially decays to 0 or it exponentially blows up. You wind up finally with a precipitation rate that's 1,000 times as big as it was in the initial state. Okay, and all of these are initialized from a value of x that is as close as we could get it to the time average value that the model chose by itself when it ran at equilibrium. So what it tells you is that there's no single answer for the same input vector at the time. It actually behaves as the convective state evolves. And we wrote down a simple predator-prey model which successfully reproduces that. And all it says is that your convective activity, instead of being determined by the grid box averages in the global model, changes in a way that's determined by the grid box averages in the global model. So you treat the convective activity as an internal process that has its own existence rather than just something that diagnostically responds right away. And when you do that and solve the equations, you get exponential growth or decay if you fix x artificially. Normally, x is constantly feeding back, and so the Hill system is stable. But we've turned off that feedback by fixing x. So you might wonder about this, it's very artificial, right? People criticize this because it was so artificial. But I think it is in the tradition of experiments like the Michelson-Morley experiment, which you could also say is artificial, but it's set up just so that it reveals the wave nature of light. You won't see the wave nature of light if you look at light from a light bulb because it's all incoherent. You have to do things artificially. So philosophically, I think that this is a way that we can make progress in understanding complex systems. So we've done other work to look at this, and we thought, well, there are a couple schemes out there that have memory in them. Maybe they do a good job. And in particular, Brian Mapes and Rich Neal came up with something called an org scheme, where they invented a new variable that they called org that they carried in the NCAR climate model that was meant to represent convective behavior in a way analogous to the new variable that we used in our predator-prey model. So we thought, okay, well, maybe we can test that. So Yiling actually built this parameterization into WRF. It was originally written for the global model, but she's written it, ported it into the regional model. And you can also swap schemes in the regional model. That's how we did the other study. Okay, and we looked at a French model down here, the LMDZ model, because it has prognostic cold pools. So it assigns some variables to cold pools, and it carries those from one model time step to the next. So it's possible for that model to have memory. So it's possible for those models to behave like this. So we tested to see if they would. Who thinks they would? Nobody's raising their hand. All right, good. You guys are good. They don't. Okay, so the black line here, this is doing the same experiment that Maxime did, where you fix the input vector to the scheme, and you look at how its output changes with time. And traditional schemes, which aren't even shown on here, would just be a flat line. They would always give the same answer. So we focused on the ones that have memory that ostensibly could, that would vary in time and that might produce this behavior. But none of them produce exponential growth or exponential decay. What they all do is they do change, but then they saturate at some value and they become happy. They approach some steady state solution, which the numerical model did not do. Okay, and moreover, they approach a steady state solution that's kind of within a factor of a few of the solution at steady state when it's fully coupled. So very different. And oh, sorry, it says in press, but this paper is out now in Jane's. Yiling did a little bit of math and we think we figured out why this happens. And it's pretty subtle, okay? If you look at our predator-prey set of simple equations for describing what the numerical model did, it gives you exponential growth of convective behavior because we assumed that the precipitation would vary linearly with our hidden variable, v, and that the hidden variable would have a source that was proportional to precipitation. So there's a positive feedback there, which gives you the exponential growth. In the org scheme, it's the same, except that they made the increase of convective activity vary with the square root of precipitation. I don't know why they did that, but they chose square root. Okay, so just, and if you solve these equations, they have a steady state solution, unlike these. So just going from p to the 1 power to p to the 1/2 power completely changes the character of the solution that you get in this particular weird experiment that we did. So our conclusion is that you can say something about the equations that you should be using by doing these weird experiments, even though they're totally unrealistic. So there's an emergent property of the idealized system. Okay, so this is all nice, but these idealized experiments are pretty far away from what happens in reality. So it begs the question, how do we, and furthermore, they're pretty idealized. They're still very idealized models. How do we get to being able to do better and improve models that will, with schemes that will work better in realistic conditions? And this brings me to stuff that's happening now, which is machine learning. So there's lots of activity now in using machine learning. Basically, people throwing their hands up and saying, well, we're never going to get these models to work. Let's just use machine learning, because look what it can do. Look what ChatGPT can do. Clearly, we can solve this problem. And one of the great successes has been that there are now emulators of Era 5 data, which will project the weather for another few days, at least as well as the ECMWF forecast system, depending on the metric that you use. So that, and companies like Google and NVIDIA are jumping in and investing resources in this just to kind of show off their chops. But meanwhile, the climate people are saying, well, this is not going to work for climate. Emulating Era 5 data, the thing's just going to, it's all about the boundary conditions, completely different problem. And so most of us have decided that we want to use machine learning on the physics, the stuff I've been talking about. So, and then keep the dynamics from the model as it is. And we really need to carefully learn the physics. So a few groups out there are trying to replace the physics schemes with neural networks, or mainly neural networks is what people have been using, but different types of neural networks. Okay, there's a few issues with this. One is it's tough to implement because machine learning is not done in Fortran, whereas all of our climate models are, not all, there's starting to be some written in other languages, but traditionally they've all been written in Fortran. Another problem is, what do you train this on? I just told you earlier that we can't test our schemes because we don't have the kind of observations that we need to test them. Unfortunately, our satellites, as great as they are, can't measure things like turbulent kinetic energy or small-scale motions in the atmosphere, which is really what we need to know. And so that's a problem. And then there's just this overarching problem of how do we bring together all these heterogeneous data types that we have. So I'm going to tell you about a project that I undertook with some colleagues a couple of years ago to try to address the first two of those bullet points. And this is with a company in Boston called STR, where my former supervisor, when I did a postdoc in New Zealand, then went to work. So we got funded by DARPA to try to build a better climate model that would address tipping points. We didn't really get there, but we got some things done. And so one thing we did was, repeating what a few other groups have done, we took output from a couple of climate models, but primarily here SPCAM. So that's the NCAR community atmosphere model with super parameterization running inside it. So instead of the traditional very naive parameterizations of the processes, it has an extremely coarse and small two-dimensional cloud. It's not cloud system resolving. It's not really, but it's still better than the physics, or it thought to be better than the physics. So that's the model that we're playing with. And we've taken the output from it, all of the tendencies that the physics is supposed to predict, and we've emulated those with a neural network. It's just a standard fully connected network, but it's deep. You need a deep network to do this, at least 7 layers I think we found. And the movie I just played before shows you a neural network. I can't even read that text. I don't remember which one of these is the neural network and which one is where does it say? Huh, I thought it said on here, but now I don't see it. Anyway, one of these is the neural network, and one of them is the actual model. And the neural network knows where it's raining and where it's not raining. It knows roughly whether it's raining hard or not hard. The exact rain amounts are often not right. But from the back of the room, it looks pretty good. So it is possible, and we're not the first people to do this. These other studies have done this. It is possible to get a neural network to learn how to behave the same as the superparameterization in SPCAM. Okay, so that's a nice first step. But then what you want to do is you want to take that neural network and you want to put it into CAM so that CAM can run with a neural network inside. And we've done that too. And we've created something which we call TorchClim, which is now a discussion paper at GMD. And I'm not going to go through the technical details of how this works, but basically using a C++ bridge and some other things, we've created a system where you can take any PyTorch-generated machine learning model, so like a neural network or decision tree or random forest, whatever you want to use, and you can dump it into CAM, and you can then dump a different one in, and you don't even need to recompile the model. So you can quickly test as many different neural networks as you want. And this turns out to be important because usually the model crashes. So there's a lot of experimentation that's going to be needed to make progress on doing this kind of thing. But we've got that, and it's available if anybody wants to use it. So here's, this is just to give you some idea of how well it reproduces the original model. On the left here is just a heating, zonal mean heating from SPCAM, and on the right is what we're calling the hybrid model, because it's a hybrid machine learning and physics. It's not the same, but it's pretty close. This is the moistening down here. And this is there's a Hofmüller diagram showing some convective organization, which is also pretty similar. So it does a not too bad job of reproducing the model that's trying to emulate. And you might say, well, and it runs at about the same speed. So you might say, well, what good is that? It's no faster, and it's certainly no better. It's not even as good, because it's only just emulating the original model. So you might say, well, what the hell good is that? And I think there are some interesting things that we can do with this. And one is the fact that you can you could use different training data sets and drop those into your model, and then you can make, in principle, you can make CAM run like the UK Met Office model. You would just have to train on those, on their physics, and then you could just drop it in if both models had this thing running. So there's things you could do. And one thing we tried was we tried cross-training on the standard CAM4 model with its dumb parameterizations and SPCAM. And what we learned was, so this panel here is the skill of the CAM4 emulator compared to CAM4, with the white color is 1. That means it's near perfect, and blue means it's not very good. So this is precipitation. The precipitation skill is not very good in places where it hardly ever rains. That's not surprising. But in places where it rains a lot, the skill is very good. And it's generally better over oceans than over land. That's also not too much of a surprise. We're one of the first groups to successfully get this to run with land in the model. Early efforts were on aquaplanets. And there were a lot of tricks that we had to go through to get that to work. This is the same thing with SPCAM. It's harder to emulate SPCAM. And I think the reason is that it's got this little model running in the boxes, and the state of that model is carried forward, so it has memory. But what we're doing here is we're trying to predict without any memory, just trying to predict what's the convection doing right now based on the state vector. So we don't actually expect that to work for SPCAM. It works fairly well, but it doesn't work as well as this one, and I think that's why. And then these off-diagonal panels are just showing what happens if you take the model that you trained on CAM4 and you run SPCAM data through it and see how well it does on SPCAM data, and vice versa. And the answer there is that if you train on SPCAM, you do a better job of reproducing CAM than if you do it the other way around. And I think the reason for that is because when you train on CAM4, you get overconfident, and then you blow it on the SPCAM data. Whereas if you train on SPCAM data, you realize, whoa, okay, this is not such an easy problem, and you actually avoid overfitting the physical system and generalize a bit better. So there's a lesson there about generalization. So a more practical related problem is, what if we have some good data? So all we've done so far is emulate a crappy model. What good is that? What we would like to do is find some other training data, train on that, and then put it into CAM, because then we can get CAM to maybe be better. And the training data that those of us in the community who are doing this want to use is high-resolution simulations. Okay, because we just don't have the observations that we need to do this, at least for convection. So we run these large eddy simulations, but they're expensive, right? We can only afford to run a small number of these in maybe some random or varied situations to make a small training data set. So what we've done here is we've said, well, what if you, using your neural network, what if you pre-train it on the crappy model output and then fine-tune it on the LES training data? And it turns out that that buys you 1 to 2 orders of magnitude less LES data that you would need. If you just want to train on LES data, you would need 100 times more. But if you pre-train on GCM data, as bad as it is, it kind of shows you something about what's going on. And the neural network learns that, and then you fine-tune it by presenting some LES data. Okay, and this is from a paper that's under review at James. And you can see here, getting tendencies, this is the skill for tendencies at individual voxels in the model, a much harder problem. This is the skill for precipitation, which is kind of like the total of what's going on in all of the vertical boxes. And it's a lot easier, but only when you get to sample sizes of at least a few hundred, then you can do this pretty well. And we can afford to run a few hundred cases in LES. That's not a problem. So I think there's potential here to make a better model. Okay. Now, again, this was all ignoring the convective memory, which I just before told you I thought was really important as a structural thing. So we need to, I think, do that. And there's a couple of groups around that are looking at this. So there's a Chinese group, Han et al., who have found that if they include previous time step value, x vectors, they get a better hybrid model. So that's a good result. But then the problem is you're putting so much extra information in. What you really want to do is you want to know, what's that hidden variable that I was talking about? What is that? What's the equation that we should have? Okay, there were 2 equations that gave really different results. What equation should it be? And this is from a paper by Sarah Shemek et al. At Columbia, where they tried to tackle this by using what's called a auto encoder and decoder to boil down the information from a tile of a high-resolution simulation down to just a few variables. So this is a really interesting and flexible way of using machine learning to achieve dimension reduction. And you can do all sorts of cool things. You can play around with the answer in low-dimensional space, and then you can generate some previously unseen state there. This is how they make fake faces and things like that using this kind of architecture. And so they found that they could predict precipitation much better if they just took a low-dimensional encoding of that field and provided it along with x. But I'm not sure what they haven't done is they haven't taken the step of actually building this into a climate model and seeing if it actually does a better job. And I worry that if your neural net isn't very good, you'll always get an improvement here, even if there weren't really any important memory. So I think there's more work to be done, but there are really interesting things happening. So what many people are doing here is, I've shown you that we're training on model physics to try to learn what we're doing. Other groups have taken a higher, like the group I just showed you, Sarah Shemek is doing this, the global CRMs, and see if you can learn, and then you make big boxes and you try to learn what would happen from high resolution. And so I've had a student who's been trying to do a simpler version of that just using Rayleigh-Bénard convection. So he's built a Rayleigh-Bénard solver. And the idea here is to see if you coarse grain your first solve Rayleigh-Bénard convection at very high resolution. That's your truth. And then imagine that you only had a low resolution solver. Could you learn some additional terms that you have to add to get it to make the Rayleigh-Bénard convection that looks like a coarse grained version of the full correct simulation? And it was all very clever. What we ended up discovering so far is that the numerical errors in solving the equations turn out to be really important. And a lot of what you're actually trying, what we found is that, at least the way we first tried to do it, which is the coarse grain just by taking, okay, these 10 grid points, average those to get this value, take these, average those to get this value. If you do that to get a coarse-grained representation, and then trying to step forward in time with your Navier-Stokes equations, most of the problems come about because of the solution errors. So there's a lot of issues that come in that we didn't expect. But I think these can be solved. So I'm going to close with some thoughts on how we can do better than just make black box emulators. Everyone so far has been making black box emulators, and then maybe with the hope one day we could have something better to emulate and then get a better result. But what I'm interested in is really how can we use this to reverse engineer the atmosphere and learn what the right equations are and learn a better conceptual model of convection. Maybe plumes is not the right thing. We can try other things. We can try having memory or not having memory or having different kinds of memory, because different, when you look at what centers like the UK Met Office are doing and others, the French, they're putting everybody kind of realizes now that they need to have some persistence, but they're all doing it in completely different ways. So nobody knows what they're doing. Can we figure out what we're doing using machine learning? And I think we can, because I think what we can do, once we have we need some nice training data, so people are generating that. But what we can then do, I think, is we can use machine learning to learn part of the system, and we can try out a physical model or hypothesis for another part of the system. And this is kind of a broadening of the concept of physics-informed or interpretable machine learning, where people think, if they build a physics equation in, it'll do better. Well, okay, what if you build the wrong physics equation in? Then presumably it won't do better. You can use this as a test of what the real equation is. Build different ones in and see when does it do better and when does it not do better. I'm hoping we can use a strategy like that and hybrid physics models. And I'm actually confident that, that in the coming years, because of the explosion of machine learning and so many people looking at it, that we will start to make significant progress. Because there's enough data out there. And once we solve convection, the next problem will be clouds. And then I'm hoping that we'll really be able to start making use of the enormous amount of satellite data that have been collected for the last 40 years, which so far I would say have still not really been exploited to correct biases in models. And you just look at a model and you look at your satellite and you see that they don't look the same. Machine learning is very good at figuring out how to synthesize fields that you can't distinguish from the real thing. So I'm very confident that we'll be able to do it. And we'll end up with GCMs that make cloud fields that look good. But I think we need to get the convection right first, because that's really what causes them. So I'll just close with those messages, saying that I think machine learning is offering us a lot of possibilities, and we should be planning for that going forward. How do we use this together with our satellite data and other data streams to push this forward, go beyond just emulating models, which is what we're doing now. And if anybody's interested in this, I just asked Beijing, and he said nobody's running GCMs here, but so probably you aren't. But anyway, there's our discussion paper. So I'll stop and take any questions.
Okay, so yeah, it'll be time for questions. I'll monitor the chat with Wingsy here, but I'll first take questions from the room. But if you have a question, go to the mic for the purposes of those online can hear your question. So I'll open up the room first. No? Everyone's sitting here in stunned silence. Nothing on chat yet. Okay, so...
You need students. Students ask all
the
questions.
Yeah, I know. So it's always been my opinion that it seems to be, with respect to this conversation about convectively resolving global models and the kilometre scale models, it seems to me that the community is sort of kind of divided, and it's all or nothing. It's either you do the high resolution or you don't. I mean, we need a hierarchy of approaches, which to some degrees is somewhat partially consistent with what you're saying. So what I'm saying is that I think the high-resolution global kilometre scale stuff that's going on, like Diamond and the next generation of Diamond, whatever that might be, are really important to do. However, it's not necessarily as maybe necessary, but it's far from sufficient to get us where we need to go. We need to go to the point where we want to answer questions like how bad will severe storms be in the future and how heavy will the rains be from severe storms in the future. We want to answer those kinds of questions. It's probably going to have to be approached from a hierarchical point of view, in my view. But you know, it's not it's not one or the other. It's not machine learned global models versus explicitly resolved models. It's some combination of all of that. And I think that's just sort of what you're laying out here, that you need, obviously you need the training sets for the machine learned tools, but you may need more than that. Anyway, that's just a general comment that I have. But
Okay. Yeah, I didn't mean to suggest that we shouldn't be doing high resolution modeling, but in fact, it's what we're doing to train.
Yeah, exactly.
But I think I hear people say things like, oh, there's no point working on model physics anymore because we'll just resolve everything. And I guess that's what I'm pushing back.
Yeah, that's
right. And I don't think that, I wouldn't trust, somebody asked me this question when I gave this talk last week at Scripps. You know, would you trust a climate model that just had a machine learning running as the physics? And I would say no, because, I mean, look at what machine learning does. You know, look at the hallucinations and lies that come out of ChatGPT and stuff. It's not a very, I much more trust something that's based on a physical principle that I understand. And so that's why I say that I think what we really want is to use AI as a tool to try to achieve that. And my worry is that if you look at the rate of progress that we've had since, in my career, since the 90s, it's just too slow. I mean, the model biases are still going to be there when everything has happened. Yeah. So we need to find a way of speeding it up, and I'm hoping that this can be the way we do it.
Brian's going to ask a question, but just before he comes up,
hi, Brian.
Another comment. You showed that result from Feng et al. You made the point about the high-res models are producing too intense rain. If you look at the tail of the distribution.
Yeah.
But similarly, the GCM, the CMIP class climate models are producing 2 orders of magnitude less heavy precipitation that at the very extreme. So if you look at the PDF of CMIP models of that PDF of rainfall, at the very extreme rains, the models are nowhere near it. So it's both ends of the modelling spectrum are a real challenge with respect to extreme rains. And that brings us to the point about what are nature's extreme rains, because we're not sure I-merge is necessarily the metric of extreme rain. So we're kind of, with respect to that metric, we're kind of really, in my mind, really in a quandary. You know, the Feng figure, you got
yeah,
PDF
sorry,
test.
I forgot how far back in my presentation
you got a PDF
this
there, so you don't have to go back to it. But
maybe it's not.
So
I think.
Yeah, but if you look at the CMIP model versions of that, which we've done, it's maybe you've got they're different by what they're with respect to the I-merge and the extreme range. They may be different there by a factor of 2, 3, or 4, something like that. They're different in the CMIP class models by a factor of 10 or more.
Well, I think it depends on how far out on the tail you go. Right?
You go out
if you look at something like the rainiest day of the year, my recollection is that the GCMs are all over the place, but that the observations are somewhere in the middle. In other words, there's not a systematic. But maybe when you go farther out on the tail, they all drop off.
You just go to the most extreme rains a model produces versus extreme rains.
Okay.
And I can show you figures of that later. But,
all right. Because even if you look here, there's a big gap at this rain rate of sort of 20 millimeters per hour, and that's a strong rain, but it's not super extreme.
I know.
And then when you go out to the super extremes, they start to diverge.
Yeah,
and some of them may be dropping below, but then you're right. I don't know if you trust I-merge.
Yeah, I know. I'm not sure we can trust it either. So, Brian.
Yeah. Hey, Steve. Fascinating talk. A lot to absorb here. So, in terms of convective memory, when you brought up the idea of the past connected to the present and the future of convection, are there certain variables or certain covariances in that state that are really driving that convective memory, and can that vary depending on the type of convection or the type of regime you're in? Like, how detailed do you get in quantifying a convective memory relationship?
Well, the limited evidence that we have from a few cloud resolving model studies is that the variability of water vapor and humidity near the surface within a grid box is where a lot of the memory resides. So the global model doesn't know whether you have a uniform boundary layer or whether you have all your water vapor over here and not over here, but the convection knows. And so the convection tends to build up this heterogeneity, and then the heterogeneity drives the convection harder. And that's what we saw happen in Maxime simulations. So physically, we kind of know that, but I think it's probably more complicated than that. And there's the issue of convective organization, which comes into it, which is what Mapes and Neal were assuming they were assuming that the memory lay in the organization of convection itself. And those things are related. And so I think we don't know. That's what I want to find out. Are there maybe a couple of variables that if you knew those, that would tell you everything you need to know about the past state. So you just have to carry those in a theory or a model, and you can do the job. I don't know what they are, though.
So really small-scale measurements of variability, especially in the planetary boundary layer, temperature and water vapor, are really key parameters.
That would be great if we had better, fine-scale measurements of temperature and humidity in the boundary layer. That would help a lot.
Cool. Thank you.
Yeah.
Okay, so you've got a question from Terry Kubar on the chat. And Terry, are you online and you want to unmute? Can you unmute? Can you unmute and ask a question? Otherwise, I'll do it for you.
Sure, I can, yes. Well, thank you for the interesting talk. Earlier, you mentioned that there are challenges that models have in representing the heterogeneity of warming and SST patterns important for teleconnections. For instance, that it might be important for the drought over the southwest U.S. I was just wondering, I didn't really see a way forward in which these current challenges or shortcomings might be resolved with some of the methods you went over today. If you could elaborate on that a little bit more.
You sound like a proposal reviewer.
Oh.
Yeah, no, I think that was really just a motivation for why I think we need to make, the models aren't good enough to do some of the basic things we want to do. I can't promise that by, fixing convection schemes, it might not solve, not every, convection isn't causing all these problems. I'm sure it's contributing to a lot of them. And I also think that if you want to fix the clouds, which almost certainly are important for SST biases, which then feed onto other biases, I think you need to fix the convection first. So that's why I'm focusing on it. So I'm not promising that I'm going to deliver a model in 2 or 3 years that's going to not have the cold, the warm Southeast Pacific SST bias anymore. But I am hoping that, using methods like this, and including an ocean, there's no reason why an ocean model can't do the same thing with the processes that they have to represent, that we might not get there.
Okay.
Next question.
Thank you.
Returning to the motivations of the talk, I was wondering your thoughts about two things. One of them, I was curious what you thought about whether there's much possibility for machine learning or some of these coupled methods to say something useful about like the human feedbacks, say response to droughts or something along those lines, whether we can look across the world and maybe combine, simulations of the atmosphere and ocean with like land surface data and data about human systems to have a better sense of how like human responses might change in response, after a disaster. And the other, maybe simpler than that, would be your thoughts about unprecedented or out of sample events and what approach might seem best for those, given our current state of knowledge and hopes for the future.
Yeah.
Thanks.
Okay, so on the second one, again, I think that the reason you want to develop a good physical understanding is precisely because if you just have an empirical model, you can't really trust it to generalize to an unseen event. I think we know that that usually doesn't work. As far as using AI to look at impacts, I am interested in the idea of, I think we're data limited there. I don't know where you would get the data to train a model that would emulate people. Maybe, I mean, there may be a way to do it. It's not I'm not a social scientist, so you might have to talk to them. But one thing I think you could do, and there's a project in our lighthouse which is supposed to do this, although it's kind of dragging along slowly right now, is to try to achieve the coupling that you need using machine learning to speed things up. So if you could build an emulator of a climate model, you could then put that into an integrated assessment model and thereby have an IAM that would have much more faithful representation of climate than the crappy low-order things that they do now. And so if you've got a good IAM and you believe that, then you can do better. If you want to learn how to do new things that none of the models are doing, then you need good data. And I don't know what that's going to be.
I was thinking something empirical maybe, but that would be hard. Some kind of satellite-based empirical.
Well, you can do downscaling. So I didn't talk about downscaling, but I've got, there's a project in Australia where we've been looking at machine learning to emulate either a fine-scale model or to downscale using precipitation observations. So we have networks of stations, and once you have that, and once you observe the large-scale variables, you can then use machine learning to go from the large-scale variables to the station-by-station precipitation observations. And so this is great if you're a farmer and you want to know what's going to happen in your field for any given synoptic condition, but you need the data. You can't do this out in the place where you got no rain gauges.
Well, thanks, Steve, again for a great seminar. I guess you have a rigid schedule, right, Steve? So.
Oh, I think it's kind of flexible because people are getting sick and dropping out.
Oh, is that right? Okay, so we're a little over time, but thanks again, Steve, for a great seminar. Okay.
Thanks again for the invitation.